Okay, another example where the math is cranked up a notch. Let's look at this. H2 gas plus I2 gas goes to 2HI gas. We've seen this reaction before. Let's change the temperature to 430 degrees Celsius. And here's the deal. You take zero point 0.5 moles of H2 and zero point 0.5 moles of I2, mix them together in a 1 liter container. Nice, 1 liter, which means what's our concentration of H2 if you have zero point 0.5 moles in 1 liter? Yeah, 0.5 molar H2, zero point 0.5 molar I2. So you mix them in a 1 liter container, calculate the equilibrium concentrations of everything, all the species, that means the H2, the I2, and the 2HI. And at this temperature, 430 degrees Celsius, the equilibrium constant is 54.3. So we look at this equation, or look at this problem, we say, okay, well, we're given the equilibrium constant, and we need to calculate the concentration of everything at equilibrium. Ice tables. All right, so no problem. Ice tables. We know, I like to just write the reaction here. H2 plus, give it a little space, I2 in equilibrium with 2HI, ice, initial change, equilibrium, draw the line. This is how I like to do it. All right, and let's put in what I know. Well, what do we know here? Our initial concentration of H2, 0.500 molar. Our initial concentration of I2, 0.500 molar. Concentration of 2HI, well, we don't have any at the beginning, 0. Change. Okay, how much H2 is going to go away? I don't know, minus X. My stoichiometry here is 1, so it's minus 1x. How much I2 is going to go away? I don't know, minus x. Note these are reactants, so I know it's negative. They go away. How much HI comes into existence? Well, it comes into existence. It's a product, so it's plus 2x. My stoichiometry tells me I get 2 HIs for every one of these guys, so it's plus 2x. So then at equilibrium, we have 0.500 minus x, 0.500 minus x, and 2x. What do we do now that we have these equilibrium concentrations, but not quite, they still have variable x in there? Well, we plug it into our equilibrium constant expression. And I highly recommend writing down the equilibrium constant expression for this reaction. The equilibrium constant expression K equals the concentration of HI squared divided by the concentration of H2 times the concentration of I2. Okay. Then I just have to put in these values. Well, what are all my values? Well, K, I've got a value for that. 54.3 is my value for K. Equals, well, what's my concentration of HI? 2x. But note, you need to square it. What's my other values here? Well, I've got 0.500 minus x for concentration of H2, 0.500 minus x for my concentration of I2. All right. Now, technically, at this point, most of the chemistry is done. It's just math now. Solve for x. X equals what? Well, wait a minute. Check this out. This was looking a little scary, but I see something here. I know that 0.500 minus x times 0.500 minus x, that's just 0.500 minus x squared. And the top I had 2x squared, and all that was equal to 54.3. I know that if I take the square root of both sides, this just gets me 2x times 0.500 minus x. equals, okay, square root of 54.3 turns out to be 7.37. Well, this isn't a problem. I've got my x's. I need to multiply both sides by 0.50 minus x. Yeah, so just, well, should we, okay, we'll just do it real quick here. 0.500 minus x, because that'll cancel. So we multiply this by 0.500 minus x. And there we go. So, all right, got little math. When we're done, we find x equals 0.393. Well, we know that's 0.393 molar. But what does that mean for us? Well, our concentration of H2 at equilibrium is going to be, we're down here. Concentration of H2 at equilibrium is going to be 0.500 minus x. So that's 0.500 minus 0.393, and that is 0.17, 0.107 molar. That's our concentration of H2. Note our concentration of I2, it's the same math. It's the 0.500 minus x, so that's going to also give us 0.107 molar, our concentration of I2. And our concentration of HI is 2x. So that's 2 times 0.393 molar, and that will be 0.786 molar. It's our concentration of HI. And now we're done with this problem. Cool. And now you're thinking, okay, that wasn't too scary, but you're feeling a little uneasy because you're realizing that just by luck, since these two were the same, we got to do the square root issue here. Let's take this up a notch, shall we? And this will be our last calculation for this video, our last example. Here's a reaction, doesn't look too bad. N2O4, oh, we've been looking at this already. N2O4 gas in equilibrium with 2NO2 gas. Turns out the equilibrium constant is 0.36 at 100 degrees Celsius. You start with 1 or 0.1 molar NO2 and no N2O4. Put it at 100 degrees Celsius flask. What are the equilibrium concentrations? Okay, ice table, started it already. N2O4 in equilibrium with 2NO2. They're both gases, so they're both in the expression. Initial amount of N2O4 is 0. Initial amount of NO2 is 0.100 molar. Note, what would you have done if you'd have flipped it the other way, made this your reactant and this your product? You'd have to flip that Kc. You could have done it that way. You could have done 1 over 0.36 and it would have worked out fine. But I'm doing it this way because, frankly, this is the way your book did it, and you will see why they did it this way in a minute. Okay, so then what's the change going to be? Well, note we have no N2O4. There's no N2O4, so we're going to get more N2O4. This is going to be plus X. All right, got that. And also note that the NO2 is going to go away, so it's minus. Our stoichiometry is a 2 there, so we'll put the 2 there, minus 2x. For every 2 NO2s that go away, you make 1 N2O4. So at equilibrium, we have x and 0.100 minus 2x. Okay. So far, so good. What's the next step? Well, the next step is you plug everything into the equilibrium constant expression. What's equilibrium constant expression? K equals the concentration of NO2 squared divided by the concentration of N2O4. Yeah, we did that at the beginning of the chapter. Using this equation, you can write out the expression. Products over reactants, stoichiometry are the powers. No problem. Well, then we just have to plug everything in. K is 0.36 equals concentration of NO2 is 0.100 minus 2x, be sure to square it, divided by x. All right, no problems there. Okay, solve for x. X equals... Okay, how do we solve for x? Oh, okay, well, we can't just square root both sides here, so... All right, so that's going to be 0.36 equals 0.100 minus 2x times 0.100 minus 2x over x. Oh, what's this, a FOIL method? It's been a while since I've had algebra. Last, I forget how to do that. But it's, oh my goodness gracious, I think we're going to have 0.36 equals 0.0100 minus 0.400x plus 4x squared divided by x. Okay. So what do we need to do here? Well, we need to multiply both sides by x here, and so that's going to give us 36x on the other side. And then, well, we've got an x and an x here, so we got to combine like terms, and we're going to find that this is going to give us 4x squared minus 0.76x plus 0.100 equals 0. And how do we solve for x here? Oh, this is a quadratic equation. Oh, man. That's right. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. What a nightmare this is. Yeah, it certainly is a nightmare. I tell you what, okay, here's the deal here, people. Once you got to this point right here and you plugged in your values into this point, how long was it going to take you to finish out this problem, knowing that your calculator cannot be a graphing calculator? Yeah, this is going to take forever to figure out this problem. And so here's the deal. On the exam, I'm not going to make you figure this out. If this was a multiple choice question, and the question is, what are the equilibrium concentrations, and it was this nasty that you had to use a quadratic equation, then the answers were going to be these types of equations. A would be this equation, B would be a different type of equation, or something like that. And now I might throw in some numerical values too, just to make sure you're keeping up with it, but yeah, I'm not going to make you run through the quadratic equation on an exam. This gets too hairy. Now, here's the deal. On the next exam, however, you're going to say, wait a minute, Watson, there was something where we had to use the quadratic equation, and you said we weren't going to have to do it. But the only answers were available was if you did the quadratic equation. The answer, nope, you're wrong. And here is the deal. If we go over to your book here, if we look at the book, the problem we were just doing is this problem in the book. Note, here's our nasty, little shiny here. Here's our nasty quadratic and all this. And then it gave you down the answers. This is page 705. And it gave you your answers down here. And you could have gone through all that math to do it. But the next section in the book is called Simplifying Approximations in Working Equilibrium Problems. So if you find that as you're going through an equilibrium problem on the next exam, that, wait, I have to go through a quadratic equation, and Watson said we didn't have to, you probably aren't simplifying your approximation. So if that is the case, then you need to use one of these techniques for simplifying it so you do not have to go through the quadratic equation.